So anyway, let's get started. I think we have a decent crowd already. Thanks for joining, everyone. So my name is Didier. I'm the technical lead for the developer community, the HPE developer community. Sorry, and this is our October Munch and Learn. And today I'm very pleased to have three speakers with us. We have Aniello from HP Labs. We have Hewlett Packard Labs. And we have Eric and Tamuz from Classic, partners of HPE, that will talk to us about the hybrid classical quantum workflows on HPE supercomputers. So before I hand over to Eric, let me just quickly make a couple of notes about some upcoming events that we're running as part of the HPE developer community. First of all, the Munch and Learn. So this is one of these. In November, we do have a Munch and Learn. Remember, these monthly talks have been started in early 21. And every month. And we have a page dedicated for these talks where we have all the past sessions with the replay links on YouTube, so you can take a look of something that you missed, and also the slides in most cases by clicking on the title of the session. And we also have all the upcoming sessions for registration. So they're usually open for registration 1 month in advance. For example, for November 20, we have our friend Ted Dunning, who actually started this series with us more than 3 years ago, coming back for a session on an access manager and how we could use this to fix our biggest security holes. This is a very interesting talk, quite generic. It's product and vendor agnostic. It's just great knowledge shared by Ted Dunning, one of our fellows at HPE. We started a second session early 22 called the Meetups to go into a little more details on particular technology or particular open source technology. And we have actually 2 sessions coming up for Meetups. And it's quite tricky to handle sessions near the Christmas break, but we'll try, and the Thanksgiving days. But we have an October 30, so that's the October Meetup, and this will be delivered by our partner NVIDIA. And registration is open for that one, so you can register immediately. My colleague Denis will paste all the links to register in the Q&A, so you can check it out and click on it immediately. The December 18th meetup will be done by a colleague of us in Italy called Antonio. And we had already Antonio talking about some LLM that he built for Atonet, but now he's actually building something interesting, is open sourcing it in the next few weeks here, called large language mesh. So he's building a mesh of models basically, and he wants to talk to you about that. And he's in this talk is joined by Tong Xu from the labs, HP Labs as well. And then we have a new series we started last month. Actually, we did a beta in August, but this really started last month, which is more like a panel discussion. So the format is a little different. We have a group of speakers. We have a host, which is not me. And we talk about different topics around AI. So the November 6th and December 11th are already planned. Unfortunately, the links are not available yet because I need to do my homework and create those things, and I received the titles only yesterday evening. And so there's going to be a session about implementing your AI breakthrough effectively, and that talks about infrastructure for AI. And then we'll have a session in December talking about the software stack, basically. So keep an eye on those panel discussions. You can watch the replay of the previous one. It's already available on that page here, Get Real with AI Jam Series. So these are called the Jam Series. All right, so that's for webinars. And then we have one additional thing that you might want to know about skilling up with us, and this is called Workshops on Demand. So we have a framework that we made available in the pandemic days to deliver workshops to during events that were virtual at that time. And we kept that functionality after the COVID period. So what we have is a catalog of about 34 workshops these days. These are all Jupyter Notebook-based workshops that you can get to 24/7, free of charge, available to anyone. And we have topics covered such as REST API, what is a REST API, Python 101, Rust 101 or Docker 101, Kubernetes 101. So a lot of 101s to get started with. And then we have also product-specific trainings on OneView, Redfish, and programming and these kind of things. So give it a try. If you do provide feedback, we have a survey at the end. It's really important we understand what's missing from this catalog and if you like the experience. Finally, I'd just like to point out that this is a community, so it just works because of the people that are part of the community, or thanks to the people. And we continuously need you to amplify and contribute. So to amplify, that's quite easy. Anybody can do that. You can join, of course, continue to join our talk if you like the subject, but you can also invite others to join. Remember, this is open to anyone, so you can invite friends, colleagues, students at university. We accept everyone. So feel free to forward the invite and the links to join these talks. We have also a monthly newsletter that summarizes everything that happens and will happen in the community. Feel free to sign up. It's one mail per month, so we won't spam you. And you can always unsubscribe. And so the link is the newsletter sign up here on the website. You can also, we have a dedicated Slack workspace entirely dedicated to developer issues. So we have channels for each of the products or projects. Some channels are really active. Feel free to join and contribute to the discussion, to answer questions or ask questions. We have an X Twitter account. You can follow us there. It's called HP_developer. And if you're an SME, you can not just join things and amplify, you can also contribute. So for example, we have a very simple system to contribute blogs. So if you feel like writing a blog, as part of our blog, you can easily, we need a GitHub account, and more or less you can write your blog or cut and paste blogs in rich text format or Markdown. We have an editorial review, we have technical review, and then let's say within a week we should be up and running on the website. So that's kind of something you can think about. Reach out if you need help, but it's pretty straightforward. We have a very complete guide for contribution that is available also on GitHub that people can read to master our content management system if there is a problem. If you're a subject matter expert and would want to participate in meetups, contact me, or participate in events. When we go to events, feel free to contact me for topics you'd like to present. And same thing, if you find that Workshops on Demand catalog is missing a topic that you are able to help with, contact us. We have a framework, so we need content. So if you have content, we'll be happy to help you put it into Jupyter Notebooks, or even better, it might already be in Jupyter Notebooks, as it's a quite popular method to deliver training. So feel free to reach out to me for these meetups and to us through some of these links here. The mail is right here, hpdev@hp.com, and you can scan that QR code for all the links on one single web page. We also have, for the HPE folks in the room, we have an internal Slack channel called Ask HPE Dev Community for if you have a question. But I think the external one is even better, because then you can help customers and you can help partners, and you can ask your questions to a bigger audience. With that, I'm going to hand it over to Eric for the rest of the session. Thank you very much, everyone.
Very cool. Well, hello, everybody. My name is Eric Garcel. I'm joined by Tamuz, also from Classic, and Agnello from HPE. And we're going to be talking about hybrid classical quantum workflows and demonstrating these on HPE supercomputers. Now, what we'll be talking about in this Munch and Learn is going over a little bit of an intro on the working relationship between Hewlett-Packard Enterprise and Classic, an overview of quantum computation to get everybody up to speed on quantum computing. Then we're going to go into what hybrid quantum classical workflows look like integrating quantum computing and HPC systems, and then go into a paper that both Tamuz and Agnello wrote that uses a nested algorithm for optimization problems called QAOA-in-QAOA. There's Q&A dedicated at the end, but if you have questions, we'll try our best to answer them in the Q&A chat on the side. Now, a little bit about our working relationship between HPE and Classic. First, Classic, we're a software development platform for quantum computers. We have this development platform that enables you to model your quantum algorithms in Python. We have a Pythonic language. You model them, you can debug them, compile your code into something that the quantum computers can understand. Then you can analyze your code, run it, review it, and of course, iterate on it. And our working relationship with HPE is we were funded by HPE's venture capital program in 2022, their what's called their HPE Pathfinder program. And since then, we've been working with Hewlett-Packard Labs to develop novel quantum and HPC applications, kind of putting both of these technologies together. And that's what we'll be showcasing in this talk. We're going to be showing a method of solving large-scale optimization problems using hybrid quantum and HPC components. And notably, this work was performed on HPE Cray supercomputing EX systems, as well as the Cray programming environment. Now, a brief overview of quantum computation. Um, at a very high level, we have a new kind of compute resource. Instead of programming and interpreting information using bits that can be either kind of in an on or off, a 0 or 1 state, you can perform computations now with a new type of uh, bit called a qubit that can hold information in a probabilistic state. So it can have a certain probability of being on or off. And this has enabled a lot of applications that have wide sweeping use cases in finance, logistics, chemistry and pharma, automotive, as well as manufacturing. Um, Now, a lot of the questions we get is, why aren't we just building larger computers? Classically, we're hitting some of the fundamental limits of classical computers, right? Transistor sizes, you can't get smaller because, your transistor is only as good as it can allow information through, right? So if you keep making your transistors smaller and smaller, your on and off won't work if your electron can just quantum tunnel through your gate. So if you keep making them smaller, it won't act like a gate anymore. So we're hitting some fundamental limits in how small and tightly packed we can make the computers. There's also huge power consumption issues and heat dissipation, right? Packing them more densely creates more heat. If you try different, architectures or geometries, maybe three-dimensional geometries instead of just flat, you also have heat dissipation issues that are getting quite complex. Now, the end goal for quantum computing is that it's going to be part of the HPC stack, along with CPUs and GPUs and TPUs. You'll have QPUs, quantum processing units. In the same way you send the right information to the right processing units where it's most efficient to run it on that processing unit, you'll just have a new processing unit that'll be very efficient for certain classes of problems. Now, going a little bit deeper into quantum computation, there's two phenomenon that make quantum computers special, right? These qubits, what we're making the quantum computers out of, these quantum particles, have two fundamental properties called superposition that allows them to be in these multiple states at the same time, probabilistically, and entanglement, which means they have the ability to share and exchange information at a distance. So the most famous example of superposition is, of course, Schrodinger's cat. Everybody likes to talk about cats in quantum. It's kind of the fun thing to do. But the thought experiment that Schrodinger came up with was that there's a box containing a cat, radioactive, and some radiation detector attached to poison. This radioactive atom has a 50% chance to decay after an hour, and there's some detector that can measure if it's decayed or not. Now, in an hour, that detector will measure it. If it's measured that this radioactive atom has decayed, it's going to release the poison, killing the cat. So, without looking in the box, the thought experiment goes after an hour, is the cat dead or alive? Since radioactive decay is itself a probabilistic behavior, the cat is theoretically in a superposition, probabilistically, of being half dead and half alive until you open the box and observe. So this is this probabilistic nature of quantum computing, that it can be in two states simultaneously until observed. There's also entanglement we talked about. Now, thinking about it kind of classically, if I put a left and a right shoe in two boxes, mix them up and send them to two locations, one in the US and one in Australia, if I open the box in Australia and see that I have the left shoe, I know without opening the box or anybody telling me any information, the box in the United States has the right shoe. So instantly, I have information transferred to me at a distance. And this is kind of a funny thing Einstein called spooky action at a distance. But it is a cool phenomenon where you can entangle information with itself. So you can do this with spins of an electron and do this with qubits in interesting ways to create kind of quantum algorithms. Now, these together allow for essentially you dealing with information in a quantum computer in this kind of probabilistic nature, and you can think about it like waves. Um, you have higher chances of getting some answers, lower chances of getting other answers, and if you put these um, together in interesting ways, you can manipulate the likelihood of getting certain answers. So when people are creating quantum algorithms on a quantum computer, you have to think about it very differently than creating algorithms on a classical computer because you have to deal with it probabilistically. So when they're built, you build them in a way that amplifies the correct solutions or what should be correct and try and minimize any solution that would be incorrect or cause a problem. So essentially, you're increasing the signal to noise ratio of correct solutions when you're building out your quantum algorithms. So that at the end of the day, when you run your algorithm, you have, if you run your algorithm 1,000 times, 999 of those 1,000 times, you'll get the correct solution. And that's how quantum algorithms are developed, trying to essentially constructively build your correct solution while trying to kind of phase out any of your incorrect or not wanted solutions. And the way quantum information works and the way you can pack information too is really interesting in that you have a huge efficiency in quantum computers, right? Um, the scaling of quantum information that you can pack into a quantum system is exponentially greater than what you can do for a classical computer. And that's why a lot of people are quite interested in this as well, not just the probabilistic nature of building it, but the efficiency of the data itself. With classical computing, right, you can either have the state be off for a bit. So if you have, 1 bit, you have 2 states on off. You have 2 bits, you have 4 states, and so on and so forth, right? But with a quantum computer, the information scales very differently. It scales like 2 to the n. So even if we're looking at the number 20 here on our graph, right? For 2 to the n, what would that be? 40 states, but what is that? 2 to the 20th power is, gosh, what is that? That is 1,048,576 different states. So you can see how quickly this scales just for 20 compute resources, right? 20 bits versus 20 qubits, it's already hugely different. So that's why when you see a lot of like news articles saying like, oh my God, these computers got to 100 qubits or 1,000 qubits, 1,000 bits wouldn't mean anything, but 1,000 qubits means a whole lot. And even incremental increases on that are huge because it scales exponentially. So just the amount of information you can pack into a quantum computer is phenomenal. And as a recap, putting out kind of all that together, what it means is that what makes quantum computers unique is kind of the superposition and entanglement kind of fundamental phenomenon. You manipulate data on a quantum computer and build algorithms in this probabilistic nature, trying to essentially increase your signal to noise ratio of your correct solutions. And the reason it matters is that you can pack a huge amount of information into a quantum computer, which means that, not for all problems, but for certain classes of problems, we'll have faster processing. And for a unique set of problems, we're actually going to be able to solve problems that we previously thought were impossible for classical computers to solve. So a lot of people are really interested in quantum computing because of these kinds of phenomenon and kind of possibilities. Now, the current state on where we are with quantum computer is that there's a lot of different competing hardware, right? There's lots of different ways to make these fundamental qubits, right? Photonic qubits. You can make it with light. You can make it with superconducting circuits. You can make it with atoms or ions. So there's lots of different companies making different ways to create the quantum computer with the fundamental quantum bits, but they're all scaling up in the power and number of these resources available. So they're all scaling up and they're all getting to a point where we're getting to kind of quantum utility, hopefully sometime soon. But they are all right now in this kind of NISQ era where I put on the title there, the noisy intermediate scale quantum, which just means these hardwares, while they're scaling in size, they're still a bit noisy. With all that in mind, a lot of the consulting companies agree, right? Boston Consulting Group, McKinsey say that within the next 10 years or so, at least this McKinsey report says that by 2035, there will be between $1 and $2 trillion of end user economic revenue to be able to be extracted from quantum computing by this 2035 mark. And that's in a couple of key industries, not in all, but in finance, logistics, chem, pharma, and automotive are some of the industries that you'll see the most near-term economic impact from quantum computing. And you can read more on this from their Tech Monitor report, their April 2024 is where I got this data from. And the ways that we're seeing kind of this more near-term utility of using quantum computing is in hybrid quantum approaches, which is why we're working here with HPE, right? There's advantages of doing quantum and classical compute in a way that uses the quantum computer for kind of very specific subsets of the larger problem, letting the classical or HPC system handle most of it or do iterations on the quantum and moving back and forth. So it allows your quantum computer to have smaller chunkable problems where you can kind of mitigate the noise issues of having larger scale quantum problem solved with quantum computers. It also allows you to kind of optimally distribute workloads. So there's a lot of kind of near-term use and utility out of doing quantum classical calculations, and that's a little bit of what Agnello will be speaking about next.
Thank you very much, Eric, for this very nice introduction, and apologies for my voice. I've caught a cold recently and it's still not 100%. So yes, please, the next slide. Thank you. Yes, so I would like to present you a vision of quantum computation for the next, let's say, 10 plus years from an HPE perspective. And I also would like to debunk a few myths along the way here, because it sounds very much like quantum computation is going to solve everything right away. But I think there is a lot to do until this point, and let's have a look at what's available right now. So we have quite a few companies who have a number of quantum computers which can be accessed by users or not. Can be accessed either through a cloud or they are co-located into a compute center already. And from time to time, you hear somebody saying, okay, we reached quantum supremacy, which means that we found some problem that only a quantum computer can solve, and we can solve it today already. But then usually a couple of months later on, you see a smart guy coming up with a classical algorithm, which turns this 600 million years needed to solve this problem into a couple of years. So quantum supremacy, at least in my opinion, is a bit far off. A bit more off. However, I very much appreciate the opportunity that quantum companies give us in giving this early access to quantum hardware, and in particular IQM. So I'm not only talking about the big players here, IBM and Google Quantum. Recently, I've also seen an announcement about the PAX company Munich, who are able to refill an optical lattice with neutral atoms and keep the operation going on for a long time. So as Eric said, I think there are a lot of technologies out there, and we still have to figure out which one is going to make the race, if any. Okay, so in the next 5 years, so let's say in the short term, of course, we hope we will still have classical computers governing all everyday work. And these classical computers are supposed to help out with the discovery of novel materials to build better quantum computers. And then in the next step, hopefully we can see quantum computers as peers, as accelerators next to FPGAs, GPUs, and high-performance CPUs. Of course, if you have problems with infrastructure, you can access all of this through the cloud. And then in the very far future, we hope to see one day maybe a universal quantum computer which is able to solve every problem. But I'm still a bit skeptical about this, because there are still fundamental limitations to a quantum computer, like the number of data that can be ingested into the quantum superposition and so on. So big data is will never be suitable for such a universal quantum computer, but who knows? Next slide, please. All right, so HPE is not directly famous for selling big quantum computers, but we have a history, a past and a present on quantum-inspired computation, which is still going on successfully. But on the other hand, the main strength of HPE relies in the construction of big classical supercomputers. Some of them are able to perform exascale computations like at Oak Ridge are gone, and hopefully we see more of these popping up around the world. Now, about 2 years ago, I don't remember correctly, we've been approached by Classic and also IQM to do some collaboration together to show the early usage of such a quantum computer within a supercomputing environment. And back then, the most natural way forward to us seemed to be to construct a classical, hybrid quantum classical workload. And the main, workload using whatever is already available on an HPE supercomputer, like the scheduler Slurm, the libraries like MPI, math libraries like Rayleigh-Sky, and so on. Now, the biggest challenge here was to find an algorithm which is not like the usual suspect variational quantum eigenvalue solvers, which essentially uses 99% of the time a quantum computer to compute expectation values, and then only computes gradients on the classical side. But we wanted to have a problem which seemed to be balanced out between the classical and the quantum part. Okay, and one of these problems is represented by a combinatorial optimization, which makes use of this QAOA-in-QAOA, which Tammuz is going to talk more about it. But we also investigated other scenarios since we believe that in the short term, we will have maybe or hopefully several quantum devices at the disposal of a supercomputer, not only one. Okay, so we're really talking about parallel quantum computation in the sense of splitting up a classical application to be executed on multiple quantum devices. And that's the point where circular knitting comes into play. And this seems to us to be quite an important thing to investigate. And a lot of work is going on from a team in the US. Okay, next slide, please. Now that's the hardware abstraction. So to say, the dream of having everything in one place. So we produced a high-speed interconnect called Slingshot, and maybe in a future iteration, Slingshot Next, we imagine to have quantum devices. Excuse me. No, it's the previous slide. Sorry. Still here. Thank you. We imagine to have quantum devices exposed to a user in the same way that we expose heterogeneous nodes, like for instance, purely CPU nodes or CPU plus GPU nodes and so on. And I have to admit here, I'm hiding quite a bit in this greenish box down here called interface. So as Eric said before, you have to compile, you have to transform a high-level program into something that a quantum device understands, and you don't get just a bit string out or something that can be easily interpreted. You get a probability distribution which has to be interpreted on the other hand. And that's where Classic can help a lot in this place, so in this interface. But of course, we also need to think about hardware implementations and how to make this more efficiently. Now, next slide, please. Right, so the tricky part in having a classical application and a quantum device working together on a supercomputer or in a data center is about the scheduling of the work. So for those of you who are familiar with a supercomputing environment, you need to tell the supercomputer what you want to have for how long. Okay, that's called the allocation. And different allocations are managed by a workload manager. In this case, it's called Slurm. And for our demonstrations we did at ISC 24 this year, we simply used a purely classical allocation where the classical application did the classical part, obviously, but then even the quantum part was a set of CPUs which were able to contact a cloud service, the IQM resonance interface, and get the data back. And this was very precious for us to understand what exactly the latency is between calling a quantum device in a cloud and getting the result back. We thought, okay, that's absolutely not going to work because you have to wait, I don't know, hours before you get the result back. But we were able to get latencies down to 1 second and less. And we were really able to run one of these QAOA squared algorithms live on the floor at ISC. So the next slide, please. Now, in a future work, we would like to have the quantum device itself as a part of a heterogeneous Slurm allocation, meaning that then we have the flexibility, or let's say in this case, we imagine the quantum device to be collocated in the same data center, so even connected to the same high-speed network. Like this, we can really minimize even further the idle time of this quantum device. Namely, you see the gap between the classical application and the quantum application. We can release the quantum application early on and let another hybrid job start earlier than expected. That's the Slurm heterogeneous jobs functionality, where we want to use dynamical process management with MPI. So again, I want to stress here the fact that we are not reinventing the wheel at all. We are just using whatever is already available on a HPE QAOA-in-QAOA supercomputer today already. And this demonstration, the demonstration using the previous slide has been done from the Lumi supercomputer in Finland. Okay, next slide, please. Now, this is the case that Tammuz is going to talk about also more into detail. It's just essentially, it's a splitting of a graph. So here we're trying to solve a max-cut problem using QAOA. And the cool thing, some guys have found a divide and conquer algorithm where you can split the graph, the classical graph into pieces and run them or optimize them independently. That's where the QAOA square comes in. And then you can recombine the graph to also compute a global solution which is closer to the optimum. And here our idea was to use MPI to offload all these subproblems to potentially a quantum device, but also a classical device. And we were using Slurm with an IQM device, using Classique to translate the mathematical problem to a quantum circuit, and everything run from the Lumi supercomputer. So now I would like to hand over to Tammuz to explain the QAOA-in-QAOA more into detail.
Yeah.
Thank you.
Can you share, please? Thank you, Aniello and Eric. That was very interesting. Now I will go into more details of what we did, but first of all, I want to give some introduction of what we have right now. So as Eric said, quantum computers suffer from error rates and have a limited number of qubits, although it's getting reduced. The quantum computers are getting way better than even 2 years ago. But every manipulation that I do inside the quantum circuit, the noise grows. And the most common way to deal with it is using variational quantum algorithms. And those will probably be the first one to have a practical quantum advantage. So the shape of those algorithms look like that. So we have the quantum circuit with some parameter inside. And then we measure, and we use the classical computer to insert the input into objective function, which is defined by the problem that we have, but it gives us also some kind of measurement, how good is the solution. Then we update the parameters to run it again and again until we are satisfied with the result that we get from the quantum circuit. As we said, we were dealing with combinatorial optimization problems that are many industries are interested in them, such as portfolio optimization in finance, vehicle routing problem in logistics, Ising model in physics, and so on. And those are defined as follow. I want to find a vector X that maximize or minimize an objective function that I have. Many times I have some constraints that I need to deal with. And those problems are very hard to solve, especially in certain cases, such those functions are non-linear, or the X vector needs to be integers or binary variables. And usually we solve them classically with with approximation or heuristic algorithms that I solve them fast, but I'm not necessarily get the optimal solution that really maximize or minimize my objective function. For example, when you use Google Maps going from some place to another place, you use these kinds of algorithms that gives you a solution very fast. And when some intuition of how it goes with quantum variational quantum algorithm, I do some iteration for maximization problem. I do some iteration, and I measure the objective function over here. And each time I go with another iteration, I maximize my objective function until I cannot get a better value. And that is intuition of how it goes. And the quality depends of how I update my parameters, or what is the quantum circuit that I have. And by the way, we in Classic we have a synthesis engine that generates the quantum circuit from a high level point of view and optimize to a certain hardware to reduce the noise and so on. And one famous algorithm for combinatorial optimization problems is called a quantum approximate optimization algorithm, which is also optimization algorithms that not necessarily give the optimal result, but give an approximated result. And it's a bit like that. It has some kinds of alternating sequence of operation that is not really relevant what are they, and we have the tunable parameters. But one thing that is important, I can, as a user, define what would be the number of layers. As I have more layers, I will get a better result, but I will be more exposed to noise inside the quantum computer. But if I have infinite number of layers, so I will definitely get an optimal result. So this is a question of how to do the best as possible. And what I want to show now that this algorithm QAOA has some potential advantage. And as I have more layers, I get better and better result. This is the result from the QAOA algorithm. And this one is the best classical approximation algorithm for the max-cut problem. And you see that this is on a simulator without any noise, and we think that this might have a potential to give advantage in the future. So some motivation to the work that we did. So we want to solve NP problems, meaning problems that I cannot solve in polynomial time, like the max-cut problem, but still the number of qubits is limited. For example, if I want to solve such very difficult problem, and I want to solve it, as Aniello said, in parallel and fast, and I want to solve them with many small quantum devices. And also initiate kind of a workload scheme of the SLAM manager to coordinate between the classical and the quantum jobs, and also to coordinate the jobs between inside the quantum variational quantum algorithms between the job of the classical and the quantum part in these kinds of algorithms. And we implemented this algorithm that I will explain later on, and we ran it with a lot of qubits. This is a lot in the quantum sense to simulate. Only HPC Center can simulate these kinds of numbers. And we also pick up the best solution from either from classical algorithm or a quantum algorithm. And we will see later that our solution approaches the best classical algorithm when the problems gets very big, a large scale problem. But I think the most important contribution from what we did is we provided kind of a testbed of initialization of the idea of that we can also use both classical algorithms or quantum algorithms by using a decision mechanism, maybe AI decision mechanism, that chooses for each subgraph if to be solved with a quantum or a classical algorithm. So the problem is the max-cut problem. Let's say I have a graph that is composed from nodes and edges between some of the nodes, and I can divide the nodes into two sets, let's say red and blue. And if there is an edge between one of the nodes, between the two nodes, and the two nodes are from the different set, so I count these nodes. If the two nodes are from the same set, I don't count this node. It doesn't matter which color are there. And the question is how to divide the nodes inside the graph so I count as many possible edges, as many edges as possible. For example, in this division, I count 4 edges. I see 4 edges that I count, but in different division, I count 5 edges. And if you think about it for a minute, you will see that you will you can't count the you cannot divide the graph in such a way that you will count the 6 edges of the graph. And for this is a very simple case, but for large problem, it becomes very difficult. And I want to give you some intuition of the QAOA square that uses divide and conquer approach. So the idea that I get a large graph, I can divide it into 2 subgraphs. Both of them solve in parallel. And then get the result. And in that way that I cannot get a very good solution, but what I can do, I can use the symmetry between of the problem that I can switch only in each subgraph between the green nodes to the red nodes, for example, in this solution, and then look at the global solution, you see that I have much more orange edges from the previous solution. And that's the idea of the QAOA square, and this also a solution that goes very fast. So as the same slide from that Aniello showed, we divide a very large graph into small graphs, solve them in parallel either by classical or quantum algorithm. Then what we do over here, after we solved, each subgraph can treat it as a node, and then I can solve again. That's the reason QAOA square. And then after I solve this again, if this end up to be green, I did not flip the 2 nodes over here. But if this ended up to be orange, I can flip between the edges, and that's and in that way I maximize the global solution of the big graph. And also this is from HPC perspective that I can solve either classically or quantumly with a coordinator the entire graph very fast. Why I say it is very fast? Because if I look at the complexity of a very hard problem of the best classical algorithm, it has these kinds of complexity, meaning the time of solution. But if I using the divide and conquer approach, I can I reduce the complexity, the time to solution dramatically, because I solve a lot of small graphs that are easy to solve with and still get a good solution. So if I look at the the main result that we have, so if I look, these are the number of different graphs with these are the number of nodes. We solved very large graphs, 2,500. And we see that the black one is a solution of a classical algorithm that solved the entire graph at once. That takes a lot of time. It's very hard to solve for a large graph. And we see that for even larger graphs, we cannot solve them with a classical algorithm. But when we solve with the QAOA square, so we see that over here we see the solution of the QAOA by the divide and conquer approach, and this is the classical algorithm, and the yellow one takes the best solution from either the classical or the QAOA square. If I look at the trend that I see as the graphs gets bigger, I see that maybe at some point over here, those two dashed lines will meet, and we will be able to see that this approach is very valuable for very large-scale problems. So we had a really nice introduction of quantum computing by Eric, and then the connection of HPC with Aniello. This to conclude the session. And the max cut can be solved with divide and conquer approach by smart and still get a good solution for the global graph. Each graph can be solved either by a classical or quantum algorithm. I think this is the main contribution that we see. And we still can solve like very large graphs in different approach. And this is and still overcome like a computational overhead, but using also quantum algorithms. And we see we just seen the extrapolation, how it can get like for very large problem, still with the amount of qubits that we have today, a good results. Thank you very much, and you're welcome to try Classic.
Absolutely, and wanted to add, if anybody's going to be at the supercomputing show at Atlanta, Georgia next month, we'll be there, HPE and Classic showing off this application live on the show floor. So feel free to stop by our booths.
Thank you, Tammuz. Thank you, Aniello and Eric. I think, Eric, you did a great job answering all the questions while Tammuz was talking, and Eric as well, sorry. Eric, and Aniello was answering the chat as well. So I think we covered everything. We have one last question, but I think it's probably relative to the graph. So I don't know if we can answer it now, which one is green. So I don't know. That was during your explanation of the graph, Tammuz, but I don't know if we can answer that one. In case, but if you
I think the green one is just a classical one where every subproblem is solved by the classical algorithm.
Okay.
Oh, I'm seeing two question chats, Q&A and the webinar questions. So
yep.
Okay, so.
Yeah, there were questions about the risk over breaking the encryption algorithm, and I think you answered this in the question, Eric, and in the chat. Agnello is basically it's not there yet. So.
Yep, that's always a popular question, right? It also matters how long does your data matter for, right? If right, quantum computers aren't going to be large enough to do this kind of encryption or decryption in any kind of a fast time frame that makes sense, probably within the next 10 years to do that. But so the question is, does your data matter for more than 10 years? Right? If your data has no value in 10 years, then you don't need to worry about it. Move over to when, if you're in the US watching this, NIST, the National Institute for Standards and Technologies, has a lot of protocols that they're investigating and recommending moving forward, like Agnello was speaking about. Move over to one of those protocols when they say to move your security infrastructure over to. And that's all you got to handle. And I'm sure companies are going to come up in the interim as we get closer to that time frame, helping you move over into those new infrastructures as well. So it's really the government contractors, kind of pharma companies that need to matter, where their data is gonna have a lifetime of more than 10 years. Those are the parties that need to worry.
Thank you, Eric. I just launched the end of session poll that we typically run at the end of each of our session. So everyone, thanks for joining. And if you could just give us a quick feedback, it's only 3 questions, probably half a second to answer. That helps us understand if we are doing the right thing in these sessions and if we should continue. And so take the time to do that. So while people are doing this, I have seen a couple of open questions again. There's a question from Konstantinos. I don't know if one of you can take a look. I don't know how to answer that. While you look at that, people ask about the replay. We will post the link on the Munch and Learn page in the replay in the last column of the table. So it probably take me a little bit, maybe next week I'll get the replay to the YouTube channel. It needs to go through our marketing asset process. So be patient, but the replay will be available.
Yeah, and if there's any questions that we don't get to during this this talk, feel free to message us after the fact. You can go to our website, www.classic.io. Classic is spelt with a Q at the end because every quantum company has to have a Q somewhere in their name. But there's a contact us button there that you can ask your questions, and we'll make sure to get back to you on those.
Thank you, Eric, and thank you, Tammuz and Agnello. I think that was a great presentation. We got lots of good feedback here already. So thanks a lot, and thank you everyone for joining. We'll see you next month for a last Munch and Learn for the year with Ted Dunning, which I'm sure will be really good. So talk to you later. Bye-bye.
Thank you.
Bye, everybody. Thanks for having us.